Thank you. I'd just like to thank the organisers for giving me this opportunity to speak here. I'm Ben. I'm a PhD student in Tom Woodridge's lab in Imperial College London, and I'll be talking today about some of our recent work looking at information propagation for biomolecular templating systems. I'll say this is work based on a paper that we've now got up on the archive, so do check that out. Our motivation here is looking at what the cell does. So a cell wants to produce proteins, but before that produces mRNAs. And there are very, very many different specific mRNAs that you could make, all the different possible sequences. Um, and each of those mRNAs um, is equally thermodynamically stable. The sequence of nucleotides doesn't affect their stability. And there are only four different nucleotides that go in to create these different mRNAs. And the cell wants to maintain only a certain number of a certain specific subset of those mRNAs at high concentrations and everything else at low concentrations. The way it does this is it has some template DNAs which bias the production of certain specific mRNAs. But also in the cell, you have these enzymes, these polynucleotide phosphorylases, which actively take these mRNAs, chomp them back up, and split them into nucleotides. And this allows the cells to recycle their nucleotides. But also, and this is an idea that goes back to Bennett in the 80s, that having these two different pathways for creating and breaking down these products, how that can actually help you maintain a non-equilibrium, i.e. biased distribution of mRNAs. And so this is our main motivation. We really wanted to explore this concept in more detail. So at a high level, we've got some set of inputs, think your monomers, which we assume the cell is able to maintain at constant concentration. Got a number of different pathways which could turn these inputs into products, i.e. polymers. And we want to know, as a function of how different the different pathways are, how biased can you make your product distribution? Now, since we assume we make some assumptions about things being held at constant concentration, we can represent our system as a linear chemical reaction network. For if you're unfamiliar with linear chemical reaction networks, they're sort of like unnormalized Markov jump processes. But here we've got nodes, and we can represent this linear chemical reaction network as a graph with nodes representing our chemical species, with an additional node here, the empty set, representing species that we're not explicitly modeling. Then here we'll work with reversible reactions, so each of these edges represents a pair of possible reactions that could occur in our system. So for example, we can go from nothing, a template comes out of solution and monomer binds to it, then another monomer comes and binds, and then that dimer separates off the template, and that's some of the reactions. We'll say that we'll work with local detailed balance to define our free energy changes in our system, where we'll use a sign convention where a positive delta G means an uphill battle to the reaction. Then you can re-parameterize all of your pairs of reactions by an e to the delta G and then an overall rate. We can take our full systems and we can represent them. We can look at how they behave. So here we've got R's for right monomers, W's for wrong monomers, T's for templates, D for destructive enzyme. And from our chemical species, we can identify some subset of those species here highlighted in the red boxes, which correspond to our products. This sets up a dynamical system. We can let that run to steady state, and then we ask about the questions about the relative concentrations of those products. So luckily for us, a very neat way to write the steady state concentration of our products is as an average over the pathways leading to their creation. So we look at self-avoiding walks in our graph from 0 to a given product. Here are R. There are four such walks shown here. And for a given self-avoiding walk, you can there's a well-defined free energy change associated with that, just taken by adding the free energy changes due to each of the reactions. And with that, your steady state concentration looks like an average of e to the free energy changes of those different pathways. we'll say now that we assume that all of our products see the same set of free energy changes due to pathways, or see an equivalent set of free energy changes due to pathways. And this is a manifestation of the thermodynamics stability of each of the products being the same. We'll also say that we imagine those free energy changes are fixed, and we wonder what happens as you change the speeds of each of these reactions. So as I said, the steady state concentrations of your products can be written as an average of the free energy changes due to pathways, and therefore each of those steady state concentrations is bounded by lower bounded by the most destructive pathway and upper bounded by the most constructive pathway. Now, since each of our products sees the same set of free energy changes, each of our products has the same set of bounds, and we can use that to look at how our distributions can be, how different biased our distributions can be. Just now, without loss of generality, we can set our upper bound just to be 1 and our lower bound to be e to the minus delta g, where this delta g then gives you the maximum difference between two pathways available in your system. So if we imagine we've got m different products, we know all their steady state concentrations. We can use this to set up a probability distribution just by normalizing by the total number of, by the total concentration. And then one metric for measuring the accuracy of your distributions is to look at the entropy, just P log P, the Shannon entropy of that. You can also think about this, or log m minus the Shannon entropy, as being, under some symmetry assumptions, as being a measure of the mutual information between your configuration of templates and your configuration of products. So what does a minimum entropy distribution look like in this case then? Well, if we minimize the entropy, it looks like we've got lowercase m products at high concentration, and then the rest of them at low concentration. It was surprising to us that this number of products at high concentration isn't necessarily 1. It's only 1 if your delta G is sufficiently large, and but in general, it's not 1. So what do these minimal entropy distributions look like? If we plot this this mutual information or this entropy drop here as a function of delta G, you see that it's roughly linearly increasing as a function of delta G until your delta G gets sufficiently large, which here corresponds to log m plus log m, after which you start to saturate. Now, if you scale everything by log m and take the limit so that you've got infinite products, you'll recover some limit where your entropy decreases linearly until you get to 1 as a function of delta G over log m, and then saturates there. And this is sort of this sort of tells you that this difference between these two pathways gives you a measure of the mutual information between your templates and your products, at least in the right limits. But bringing it back to the title of why is this low cost? Well, if you look at the distribution or the configurations which give you minimum entropy, it doesn't actually correspond to having things being created by the template and then destroyed by the enzyme. Actually, the products you want at high concentration, those are just equilibrating with the template pathway, the low cost pathway, just back and forth here. And those which are being those who want at low concentration just equilibrate with the enzyme pathway, the high cost pathway, just back and forth here. And so these things are sort of like a pseudo equilibrium, and actually there's no cost. You're not going round in cycles, you're just going back and forth. So not only is there no lower bound on the free energy it takes to maintain these distributions, these biased distributions, but actually if you see some flux, that's sort of a hallmark of being away from optimal behavior. But with that, I'll finish up. I'll just thank my group and Jenny and funding, and leave the link for the archive up here. Thank you.